Patty Simpson with Simpson Math. In this video, we're going to talk about symmetry and functions. First, I'm going to define for you even and oddness in functions, and then we're going to look at 3 examples and determine if they are even, odd, or maybe they're neither. So first, the definition. The definition of evenness tells us that if, when we have a function, we input a negative x into that function, if our output then is exactly the same as our original function, then we say the function is even. And that tells us that the graph then is going to be symmetric about the y-axis. So if I fold it on the y-axis, all the points on one side would match up to points on the other side. If, on the other hand, when I input a negative x and I get out a negative 1 times my original function, then we say that function is odd. And that oddness tells me that the graph is going to be symmetric about the origin, you know, that 0, 0 point on our graph. So here, let's look at 3 examples. In this first example, I'm going to determine if it's even, odd, or neither, and I'm going to use my definition to do that. Just by substituting in everywhere I see an x, I'm going to substitute in a negative x. And then I'm just going to simplify it and look at my output and start comparing it to my original function. So there I've input a negative x everywhere I saw an x. And now I'm going to simplify. Negative x squared just gives me x squared. When I look at this function, notice that it is exactly the same as my original function. So when it is exactly the same, we say the function is even. And it tells me that this function is going to be symmetric about the y-axis. In fact, if we looked at a sketch of this, just a rough sketch of this particular graph, we would see that there would be an asymptote on one side. And if I fold it on the y-axis, there would be an asymptote exactly on the same on the other side. And we would see that there would be a parabolic shape that would look something like this, where if I fold it on the y-axis, the sides would match. And even on the outsides there, they would be symmetric as well, so that if I folded it on that y-axis, they would match. So this is an example of an even function. Let's look at this function. I'm going to do the same thing. I'm just going to input for my x values a negative x everywhere I see an x in that original function. And then I'm just going to compare it to my original and see what I have there in the end. So when I input that negative x, I get out on top a negative 2x divided by, well, that becomes x squared minus 4. Notice that if I took a negative 1 and multiplied it times that original function, let's do that. Let's take a negative 1 and multiply it times my original function. So if I'm just taking a negative 1 and multiplying it times 2x over x squared minus 4, remember when I multiply that, the top would multiply times the top and the bottom would remain the same. So that I would end up with a negative 2x over x squared minus 4, because on bottom I'm just multiplying by that 1. So when I input a negative x, I got out a negative 1 times that original function. We say that this function is odd because this is equal to a negative 1 times my original function. We say that this function is odd. That tells us that this graph is going to be symmetric about our origin. So if we look at a sketch of this graph, just a rough sketch, it would look something like this, where again I would have asymptotes here and I would have asymptotes there, so that it looks like, you know, maybe I'm folding on the y-axis, but really if I fold on this origin, this piece would end up over there and this piece would end up over there. And then here on the outsides, I would end up with shapes like this on the outside. So again, if I folded on the origin, these pieces would match with those and those pieces would match here. And then in the middle, I would end up with a shape like this. So again, if I folded on that origin, the pieces would match. So this is symmetric about the origin. So that is an example of an odd function. Here, I'm going to, on this last one, do exactly the same thing, and then we'll compare it to its original. So I'm just everywhere I see an x, I'm going to insert a negative x. I'm going to substitute in a negative x, and then we'll simplify and compare it. So a negative x minus 2 is just minus x minus 2. And then on bottom, I have x squared minus x minus 6. So we notice that this is not identical to our original function. I have a negative here and a negative there. So it is not even. So then I'm going to look to see if it's odd. Well, if it's odd, that means that if I multiply this function by a negative 1, I would end up with that. Let's test it. Let's take our h and multiply it by a negative 1. So I'm going to do a negative 1 times that original function and just see what I get. And remember that when I do that, this negative 1 could be rewritten as negative 1 over 1. So I'm multiplying a negative 1 times the top and 1 times the bottom. And I get negative x plus 2 over x squared plus x minus 6. Notice these two do not match because of that plus sign in the middle. And then also we have a negative there on the bottom that shouldn't be there. We could also say, instead of doing a negative 1 over 1, you agree that it's also 1 divided by a negative 1, that's also a negative 1. This is another way to look at it, but I'll show you that it doesn't matter. It's still not going to work. If I multiply on top, I've got x minus 2, and on bottom, I have a negative x squared minus x plus 6. Again, notice that those two do not match. So since it's not equal to the original and it's not equal to 1 times that function, we say that this function is neither even nor odd, and that tells us that it is not going to have symmetry. So there's a little discussion on symmetry and functions. Math Made Simple at Simpson Math. Thanks for watching.